Now, the one thing that's different about integrating this f dot delta s sub I, as opposed to integrating a density function or an arc length, is that you're not any longer interested in the magnitude of delta s sub I. You're interested in the dot product of some vector function with your delta s sub I, and that f is a vector function, yes. Okay? So ultimately, for this integral, you're going to be doing your r vector dotted with your delta s sub I vector. And it's going to look something like this. You got f of xy on the path x of ti plus y of tj. On a given subinterval, delta t sub I, you have your delta s sub I vector, your x prime of t sub I star times I, y prime of t sub I star j, times your delta t sub I, just as before. And this, of course, is approximately equal to your delta xi times I plus your delta yi times j. So that your f dot delta s sub I is f dotted with this vector. And before we had a ds, remember, just to contrast it, that our ds was the square root of dx dt quantity squared plus dy dt quantity squared times dt. Okay? Here we didn't have the vector, we just had the magnitude of this vector times r delta t, and that was our ds. Okay? But here, again, we have to do a dot product, and we're not doing this. Okay? So you want to make that distinction. Okay, well, we're going to go on and then look at a spiral path between our same two points.